Hi, I'm Mason Vale from Boise State University. In this video, we're going to look at an array-based implementation of a list interface. A list interface defines the mental model for a list from the user's perspective in terms of the operations and the expected behavior of each of those operations for a list, but it makes no assumptions about how that list will actually be written in code, how the implementation of this list will actually work. So the user of the list doesn't have to know anything about how a particular class, a particular implementation will work internally in order to interact with it. It's important though to realize that even though any implementation of a list, any good implementation of a list, will have all of the functions, all of the functionality that was defined in that interface, it's capable of doing all of those things. There is no one single best implementation of a list that's the most efficient under all circumstances. So the internal management of our particular list implementation is going to affect the overall efficiency of each individual interface method and how it uses memory. If we think about some of the features of an indexed unordered list, it's a linear data structure, a sequence of elements where each of the positions for these elements are represented by an index position. So the first element would be at position 0 and the second element would be position 1 and so on. It seems like it would be pretty obvious that we could store these elements in an array where each element is placed in the corresponding index position of that array, because arrays are also organized in a linear fashion and they already use indexes. So if we just put every single element from the list in its corresponding index position in an array, it seems like we could use an array to manage the concept of a list. It also provides us, if we do that, with very fast lookup and access of elements by their indexes, because arrays are very fast. They have constant time access to their elements by index. So it seems like a good mapping. It's easy to visualize how we could put list elements inside an array. There are some downsides though. Remember that arrays never change size. They don't automatically grow or shrink to fit their contents. Once you create an array, it's a fixed size. So if you need a different sized array, you have to create a different sized array and copy elements into the new array. So since we're dealing with a fixed size container, the array as the container for the list, and it doesn't automatically grow or shrink, we're probably usually going to be working with an array that's larger in capacity than the number of elements actually in our list. The array length and the list size are rarely going to exactly match. We also recognize that elements that are stored inside of an array don't just shift around. They don't just move themselves around. Each element is placed in a specific location. So in order to do things like insert new elements somewhere inside the existing list and keep all the elements in their correct indexed position, we may have to shift some or all of our elements that are currently stored in an array back by one position to make room for an insertion. Likewise, if we remove something from an array, lists have no gaps. There's no gaps. So if I pull something out from the beginning or middle of an existing list, in order to keep elements in their correct index positions, we're going to have to shift some or all of those elements forward by one index position to close gaps. So there is this concept of shifting that's present in an array in order to manage the elements. So if I put elements in their corresponding index positions in an array, I get some advantages and I get some disadvantages. But this is a fairly clear mental mapping between the concept of a list and the concept of an array. In this slide, we can compare the abstraction from the implementation and get a little clearer picture of what's going on. Above the green line, we have the user's perspective, the abstract data type perspective, or the interface perspective. This is the highly abstracted viewpoint. From here, we visualize a list simply as a consecutive sequence of elements. So A is the first element, then B, then C, then D. And there's no concept and no interest really in how code is managing these things. There's no management concept. The elements simply are in this order, and I interact with them through the interface methods. Underneath this green line, behind the curtain, inside the class or the implementation of the abstract data type, we see the programmer's perspective, the internal perspective. This is how I'm going to manage the data so that the user gets the impression that the abstract data type is working correctly. So here's where we see our array that holds elements of type T, whatever the generic type of this list happens to be. And we see that in the same corresponding indexes that the user would imagine for elements A, B, C, and D, we're using those same index positions to store references to A, B, C, and D inside of our array. We also see that the array in this case has more capacity than we have list elements. This array has capacity for 6 elements right now, and the list only contains 4 elements. So we have to do something behind the scenes to represent where's the end of my list. Where does the list end? Because that's not going to be the same as the size of the array. In this example, we're using a variable that I'm calling rear, and rear is an integer that tells me the index of the next available index position inside of my array. Now, the nice thing about using the next available position, not only can I use that if I decide to add to the end of this list, but by using the next available index position, that means I also happen to have a variable that represents the current size of the list. Rear is 4 in this case, which is the next available index. It's also the number of elements in my current list. I can use this rear variable in combination with the array's capacity to detect the point at which I run out of space in the array that I'm using right now. So we can use this rear variable when it equals the capacity of the list. That's my cue that I need a bigger array if I'm going to add anything new to this list. So now we're ready to start writing an implementation of an array list. We'll begin at the very beginning by implementing our list interface and defining our instance variables, both for the array and for our rear index. We need to initialize those variables in our constructors. So I say constructors because an array list often has 2 constructors. One is our default constructor that we would use if we really have no idea how many elements we're going to place into this list. So sometimes that initial capacity could be 10, it could be 100. We simply have to pick some value for our initial capacity. Our second constructor, though, is used when we have some idea of how large our list might get. So we'll supply an initial capacity that's large enough to hold the number of elements we expect. So if I expect that I'm going to put 100,000 elements into my list, I'd like to define the array originally large enough to hold those 100,000 elements so that I don't have any unnecessary overhead in the middle of my add methods where I run out of room and have to grow my array. And then finally, I'm going to identify some high value, easy to implement utility methods that I think I'm going to need to support my other methods. So things like the toString method would be useful to implement early on so that I can use it in debugging. I can see the current contents of my list. The size method and the isEmpty method might be used by other methods to detect a condition in which they might need to throw an exception. And the indexOf method might be useful for me when I'm trying to identify the location of some target element inside my list. So these are methods that are relatively easy to write, but they're also going to be things that I might need in other methods early on. Here I've created a basic class with the name that I want, and it has a very basic Java doc for the class so far. I went ahead and put in a to-do comment for each of the things that were on the previous slide. So we need to implement our interface, we need to define our instance variables, we need to create our constructors, and then we will identify and implement some of the most immediately useful utility methods. So up here at the top, I have my IUArrayList, but I'm not implementing my interface yet. So I need to say that I'm implementing implements my indexed unsorted list interface. And we have a generic that's defined by this indexed unsorted interface, list interface, and my class needs to have the same generic that I'm declaring for my interface. So these should match. Now, right now, I'm seeing that IUArrayList is complaining because I just signed a contract. When I say I implemented IndexedUnsortedList, that puts me on the hook to supply all of the methods that were defined in that interface. So since I don't have any methods yet, I'm going to go ahead and use Eclipse's auto-generate functionality to add those unimplemented methods. So it's doing that. I get now a stub, a minimal method for each one of the required methods from the IndexedUnsortedList interface. It also moved all of my comments to the bottom, so I'm going to grab those and move them back up to the top. And now we've implemented our interface, so I can get rid of that first to-do item. None of these methods at this point actually do anything. Anything that has a void type, there's no code, no functioning code whatsoever inside. When a return value is required, for example, remove first is expected to return an element of type T, my generic type. It has to return something, so it returns a null, which is never going to be what I want. But it's in there, it allows the code to compile. Some of these require an integer, they're all automatically returning a 0, which sometimes is the correct answer, but usually not. The method is not functional. Some of these require a Boolean, they're always returning a false. So when I auto-generated the code, it was minimally compilable code, but it's not functioning yet. So we need instance variables now. The instance variables that are required for our list were an array of type T. I'm going to make it private to enforce encapsulation. The array is of type T. Whatever our generic happens to be, that's going to be the type of the array that I want. And to distinguish between the array that manages a list and the list itself, I'm going to make sure I call this array and not list. I don't want to misrepresent and make us equate the array with the list. The array is how we're managing the list. So I have an array, and I also need my rear index. So I'm going to create private int rear. So we've got our two instance variables that we know of so far. And that's all we've got so far. So now I need constructors. I need a default constructor and I need a qualified constructor that takes in an initial capacity for this array. So this is where we're going to create the actual array and initialize rear. So I'm going to start with the default array list. Doesn't take in any arguments. It's the default. So at this point, I need to create an actual object to hold all of these elements. I need to initialize the array equals. What I would like to be able to do is say I want a new array of type T with some capacity. And several things are going to happen here. I don't know what capacity to use. I'm going to pick 10 pretty arbitrarily. Almost any value you pick is okay, but we have to pick something. So I'm going to say 10, but I don't like hard coding in a size. I don't like numbers that have no meaning attached to them. So what I would rather use instead is a constant, something that has a name so I know what I'm talking about here. It's the default capacity. So that's better. So let me declare as a constant default capacity. And I'll set it equal to the 10 that I wanted. So that way I don't have numbers running around in my code that have no explanation. So that's default capacity. All right, I'm getting an error from the compiler that tells me that I cannot create a generic array. So it's interesting. I'm allowed to declare that I want a variable that is a generic array, but I can't call a constructor on a variable, an unknown array type, an unknown variable type. So I'm going to have to jump through a hoop here. And this is just a quirk of Java, the way they implemented generics. I have to jump through this hoop. So I have to declare an array of a known data type. And I would like to be able to configure this later to hold any kind of data type that I want. So the only known data type that's capable of holding anything, whatever T ends up being, is object with a capital O. The object class is at the root of all inheritance hierarchies, so any item can be assigned to an object reference as a polymorphic object reference. So object is the only array type that's capable of holding anything. But I can cast that array that I was allowed to call. I was allowed to construct an array of type object. After I've created it, I can cast that array to an array of type T. So the issue was that I couldn't call the constructor on an array of type T. But once I have an array that's capable of holding anything, I can cast it to an array of type T to enforce type safety. Now, as soon as I've done that, I'm warned that this is a narrowing conversion. It's a potentially dangerous cast, because anything is storable in an object reference, but not everything would be storable in whatever I declare type T to be. Well, I just did this. I created an array. I've not put anything in it. This is a safe cast. So I'm going to go ahead and suppress the warning on an unchecked cast, because I know as the programmer that this is a safe thing to do. Just in general, if you know why you're getting a warning and you are confident that you understand that warning, you've acknowledged it, and it's safe to do, you can feel safe in suppressing a warning. If you don't understand why a warning is being given, don't suppress the warning. Okay, so we have a default constructor that initializes my array. I also need to specify rear, and rear is the next available index, and it's also the size of my list. So in the beginning, rear must be 0. I have no elements, and if I add an element, the only place where it could end up is in index 0. So rear equals 0. That's my default constructor, the one where I don't know in advance how big I want my list to be. I also need a qualified constructor. Same name. The name of the class is the name of my constructor, but this one's going to take in an initial capacity. I'm going to specify in advance. I know how big I want this constructor to be. So in this case, instead of using my default capacity, I have to jump through my hoop here. I'll declare a new object array, this time using the capacity that was passed in. So this is how if I know in advance I want to put 100,000 elements into my array, I can specify 100,000 elements, and then my array will definitely be big enough to hold the elements I'm expecting. And rear is still equal to 0. Now, if I observe this, I'm going to suppress my warning again. If I look at these two constructors, I realize that the only difference here is the capacity that I used. And even though it's a minor point, I'd rather not have the same lines of code repeated in multiple places. It's code duplication. So I can recognize that the default constructor is just a special case of the qualified constructor. So rather than duplicate these lines of code, I can call the qualified constructor from the unqualified constructor and use my default capacity as the initial capacity. And at this point, I don't need this comment or this warning anymore. What I do need are Java docs. So I'm going to auto-generate some Java docs. This is the constructor that uses default capacity 10. I'll go ahead and tell the reader what that default capacity was. And for my qualified constructor, I'll point out that the initial capacity is the initial array capacity. So this is the constructor that uses the specified initial capacity. Okay, so we've gotten through our, we've implemented our interface, we've declared our instance variables, we've got our constructors that initialize these instance variables, and now we'll turn our attention to looking through the methods that I need to implement and identify some useful ones. So I said what those methods were. We'll just go through one of them for now. I know that for methods that are coming up, I'm going to want the indexOf method. So this indexOf method will be useful because it's going to help us think about navigating through the elements of a list. Remember, my elements are actually in the array. So if we look back at the interface and the description of what the indexOf method is supposed to do, we see that it returns the index of the specified element or a -1 if the element is not found in the list. So in the event that the element that I'm looking for is not in the list, we'll return a -1. So I'm going to start out by identifying the return index as -1. In the end, I need to return the index. So if I find the element between the time that I declared that the index is -1 and the time that I return my index, if I find it, I'll replace index with the actual index. But until I find the element, I'm going to leave it at -1. So in between here, I need to start hunting for the element, my target element. So I'm going to loop. I'll write a for loop here, and I'll begin with index I at 0. So I is going to be the starting point, the original index. So 0 is the very first index in any list. And I'm going to continue as long as I is both less than the size of my list, which is represented by rear, but it also, I'm going to quit if index is ever greater than -1. If it's 0 or greater, that indicates that I've updated my index and I'm ready to bail out. I don't need to continue looking. And we'll continue looking until we get to the end. So I have a two-part condition that would break me out. I'll quit when I run out of elements to look at, and I'll also quit if I end up finding the element I'm looking for and update index. So here's our condition check. If the element at my current I, my current index I in the loop, is equal to, matches the element I'm looking for, then index equals I. Means I found the location of the element that I'm looking for. And so index equals I. So now I'll be able to bail out of this loop. I'm intentionally using the .equals method to compare elements rather than equals equals. The equals equals operator is comparing object references, the exact object reference. It's checking to see if the object that I'm looking for is the same object in memory as the one that's located in the array. And searches often are using elements that look like the element I'm looking for. The user doesn't already have that element. The user is trying to locate an element that looks like this inside the array. So I want to use the .equals method, so I'm doing fair comparisons for something that is equivalent to the element that was passed in rather than the same object. Okay, so I have an indexOf method. Now, if I were writing this completely, I would go ahead now and finish the size method, the isEmpty method, the contains method. I would probably also include first and last, just methods that are relatively easy to write so that I have something to work with, and also methods that I expect to want to use right away in other methods that are utility methods for other methods. Now we'll turn our attention to what it takes to insert an element into an existing list. So this corresponds to the addAfter method from our interface. From the user's perspective, if they want to insert an E after existing element B, we just imagine that the list accommodates that insertion. The E is simply inserted in between the B and the C. So from the user's perspective, that's all it takes. When we look at it from the array perspective on the inside of our data structure, however, we see that a lot more work is involved in order to allow that insertion to happen. So first of all, before we can insert anything into an existing list, we have to know that we have enough capacity. Now in my example here, there is sufficient capacity, but if there wasn't, I would have to expand the capacity by creating a new array with more space and then copy all of the existing elements into the new larger array. I also need to find the element in the list, so I don't just automatically know where this element is. So I would have to locate the B, and then I would have to shift all of the elements that follow B back by one index position to make room for me to insert the new element E after the B. So all elements following B have to be shifted backwards. Then I can finally insert the E at its intended position and update my rear variable so that I know where the new end of the list is. So for our code for the addAfter method, we have to begin by locating the target element, the one we're adding after, and if we don't find it, we throw a no such element exception. Once we get past that point and we have a target element location, we have to check for capacity and expand that capacity of the array if necessary. Then we're ready to shift all elements that follow that target element backwards by one position to make room for the next element, and then we finally can insert the new element and update rear. Let's write that algorithm now into our code. So I'm here in the addAfter method, and I've copied in the steps from the previous slide so that we can start filling in this method. We start by having to locate the target. We need to know where the target element is. So this is where our indexOf method that we wrote previously can come into play. So I'm going to get the index of the target. I'll call it target index. And I'll get the index of that target. So we'll hunt for the target inside our array and find the index. So we know that if the element is not found, if the target element is not found, indexOf would return a -1. So the way we'll detect if we didn't find it is if our target index is less than 0, because 0 or greater would be a valid index. So if the target index is less than 0, that's our cue that we did not find the target element, and we should throw a no such element exception. So I'll throw that, throw new no such element exception. And this is the first time we've thrown a no such element exception, so we're being prompted to import it. I'm making sure I'm getting the no such element exception from the java.util package. So it's imported now. Okay, so we've located the target, we've thrown the exception if we didn't find it, and now we need to expand our array capacity if necessary. So the way we were recognizing that we had run out of space, the way we've described this, is if my rear variable is greater than or equal to, it should never be greater than, but we'll say greater than or equal to array.length, the actual capacity of my array, that's our signal that we've run out of capacity and we need to make our array bigger. So the way I can make my array bigger is actually to create a new array that's twice the size of the old array. So I could declare a brand new array that's got a larger capacity than my original array, and I could write a loop to copy all of the contents of the old array into the new array, but there's a class, a utility class in Java called arrays that contains a useful method that does all of that for me. So I'm going to assign my array reference to a new array coming from the arrays class, and it has a method called copyOf. I'll pass in the original array and the new length that I want, and behind the scenes, the arrays.copyOf identifies the type of the array and creates a new array of the same kind, and it uses the new length that's passed in, and it writes that loop for me in the background to copy all of the elements out of the original array into the new array, and it returns a reference to the new array. So if I use the returned reference and store it back in my array variable, I'm keeping the new copy. I'm keeping the new larger copy. So the array I want to copy is array. And the new length that I want, I'll follow a standard heuristic, a rule of thumb, and I'll get a new array that's twice the size of the old one. So array.length times 2. That gives me a new array with twice the capacity. By doubling repeatedly, every time I need to expand capacity, very quickly, no matter how large I need this array to be, I'll eventually arrive at an array that's large enough. Pretty quickly. I won't have to do this too many times. So before I move on, I realize this logic right here is going to be something that I have to do every time I add, regardless of which add method I use. I always have to check and expand my capacity if I've run out of room. So this little block of code is going to be reused repeatedly. So it's a good candidate for being pulled out into its own private utility method that I could use over and over again in other add methods. So I'm going to do that. I'm going to grab this code. I'm going to make it its own method. And I'll put this up above all of my add methods where I know that it's available to me when I start looking here. So I'm going to make a private utility method. It doesn't need to return anything. And I'm going to give it a descriptive name. I'm actually going to call it expand if necessary. And I hope that that name implies that I will only do work if I actually need to do work. And I'm pasting in that code that we wrote. So every time I call expand if necessary, we're going to check the current value of rear against the current array length. And if it's not big enough, we're going to make our new array twice the size of the old array. Double capacity, array capacity, if array is full. That's my description of the expand if necessary method. So back in my addAfter method, I'm just going to call expand if necessary. Oops. Expand if necessary. There we go. And it does that work for me. So once I get past that method, I know I have enough room. If I needed more room, I made more room. If I didn't need more room, then I already had room in the first place. So now I need to shift all of the elements following target index back by one index position. And I need to be careful when I do this that I start in the right location and I end in the right location, and that I'm copying in the right direction. I need to move all of these elements backward. So one possibility would be starting at one more than my target index and copy those elements backwards as I move backwards. But that would result in taking whatever element follows my target element and making a copy of that element and copying it over every position until I reach the end. So that's the wrong direction to move. What I need to do is actually start at the end of my list, at the rear position, and move forward through the list, move forward toward the target index, copying elements backwards as I go. So I need to make sure that this is correct. Strong word of advice: if you draw pictures of what you're trying to accomplish, you'll have a much easier time visualizing what it is you're about to do, and you might catch yourself before you accidentally start copying elements backward over other elements. So I'm going to start at the back, and I'm going to try to be consistent here and always use my I indexes as the index I'm going to write into. So the first index I'm going to write into as I move elements backward is rear. That's the next available index position. I'm going to stop when I reaches target index +1. So I has to be greater than target index +1. Target index +1 is the last value I'm going to grab and move backward as part of the shifting process. So I has to be greater than target index +1, and I'm moving forward, so I'm decrementing from rear back toward target index. And for each of those, I'm writing into index position I the value that's in front of index position I. So array index I is being overwritten with the value from I -1, the value in front of index I. So after this loop, all of the values that follow target index have been moved back by 1. Okay, so now we've opened up a space. I have a duplicate of target index +1 in both the target index +1 location and the target index +2 location. So target index +1, I can overwrite that with the element that I'm supposed to insert. So target index +1 equals the element, the new element that was passed in. So we've inserted a new element. That means we have more elements, and the rear value, the rear index, has something in it now. So rear has to get incremented, rear ++. I have a new element, and the next available position is 1 greater than the old rear value. So now we're going to think about what it takes to remove an element. So we'll look at the remove method that takes in an element argument, finds that element in the list, and removes it and returns it. So from the user's perspective, if they choose to remove B from an existing list, the B is simply plucked out of the list and the list contracts to fill in that gap. There are never any spaces inside of a list, no gaps. So the list becomes ACD instead of ABCD. In order to make that happen inside the list, we have to take the element that we've located, element B, and remember it because we're supposed to return it at the end. So we locate that element, we remember it in another variable, and in order to close a gap, we have to shift elements again. So all of the elements following B need to be shifted forward by one index position. So whatever comes immediately after B will overwrite B, and whatever comes after that will overwrite C, and so on until we make our way to the back of the list. So this time, in order to make that happen, we're going to start at our target index, the place where we found element B, and we work our way toward the back of the list, toward the rear of the list, copying elements back as we move toward the rear of the list. Now, at the end of this, we will have a duplicate element in the very last position. So the value that is currently at rear -1 will have been copied both into the rear -2 position, and it still exists at the rear -1 position. So we need to get rid of that duplicate, make that position equal to null so that we don't have a duplicate copy. And that just helps us to prevent possible memory leaks in our program. Now, after doing this removal, we have fewer elements than we did before, and we want the old rear -1 index to now be the rear of my list. So we need to decrement rear. And after all of that, we're finally done. We've removed the B, and we can return the reference to B from the remove method. Making this work in code, just reviewing again, we start by locating the element that we want to remove, and we store that value for later return. If it turns out that we can't find that element, we need to throw a no such element exception. If we get past that point, we found it. We write our loop to shift all of the elements from our location, our index that we located. All elements from that index back to the end are shifted forward by 1. So we're overwriting our removed element, and we don't want to leave any gaps. After we've pulled everything forward with a shift operation, we need to clear our duplicate last element. Then we can decrement rear, and we finally, at the end, can remove return the removed element. Okay, so let's write this into code. Once again, we're going to use our indexOf method to locate our target element. So let's grab this thing. Let's store this. Int element index equals indexOf element. So we know that the indexOf method will give us a valid index if we find it, or a -1 if we don't find it. So if element index is less than 0, we did not find it, and we should throw a new no such element exception. So if we get past that point, we have a valid index. We need to store the element that's at that location before we start overwriting things, before we do any shifting. So the type of element that's stored in our list is elements of type T. It's our generic type. We don't know what that is inside our code here, but it's an element of type T. So I'm going to call this value retval, short for return value. You can actually call it whatever you want. Retval equals the value from the element index that we just located. Element index. So we're storing our reference to that element before we overwrite it. And at the very end, that's the value I'm going to return. That'll be our last step. We'll return the value we stored. So now we need to shift all elements that come after our removed element. We need to shift them all forward by 1. So let's write a loop. And I'm going to try to be consistent again, where I always use I as the value I'm writing into. So the first index position I'm writing into is my element index. We're working our way backward, so I has to be less than rear -1. and we're moving backwards, so I++. We're moving toward the rear, so it's I++. So the last index I'll write into is in front of the last element that was in my old list before I started shifting. Okay, so array at index I, that's where I'm writing into, equals the value that comes after array at index I. So that's array I plus 1. Reaching back and pulling forward. Okay, so after this, I have a duplicate value in rear -1 and rear -2. So I want to clear that duplicate value. Array at rear -1 is null now. So I don't have a reference in both of those locations. Decrement rear, I have fewer elements, and the old rear -1 position is now the actual rear of my list. And finally, we return our removed value. So there's a basic remove method. Although we aren't going to write out every add method and every remove method here, you can apply the principles that we showed in the addAfter method to the remaining add methods. You simply have to shift if necessary to make room for the location where you need to put the new element. For the remove methods, you need to remember the element that's about to be removed, shift elements forward, remove any duplicates, decrement rear, and return the removed value.